the results and then some technical details, and I'll finish with a conclusion. So here we are dealing with inconsistent databases, and inconsistency is only with respect to primary key constraints. So there are no other constraints involved. And then some notation. So I call a block. A block is a maximal set of tuples that agree on the primary key. So these are maximal sets of inconsistent tuples. And a repair is just any subset that you can obtain by picking exactly one tuple from each block. So it's maximal consistent subset. So as an example, suppose you have a relation where you have the town, the country, and the Michelin rating. And here you have two blocks because there's uncertainty about the number of Michelin stars of Mons. It can be 1 star or 2 stars. And so in this case, I have 2 repairs because there's one block with 2 tuples, right? So that's the data model we are considering. It's very simple. And now the problem we are studying is problem certainty Q, where Q is some fixed Boolean query. And so the input to the problem is a database that can be inconsistent, so there can be primary key violations. And the question is whether Q is true in every repair of the database. So for example, if I take the same database and we are asking whether Mons has 2 stars, that's not true in every repair, so the answer is no. And if we are asking whether it's certain that Mons is in Belgium, then the answer is true, because in both repairs, Mons is in Belgium. So this leads to a complexity classification task. So giving some interesting class C of queries, we are interested to knowing, can we pinpoint the data complexity of certainty Q for each Boolean query Q in the class? And a second interesting problem is, if we take certainty Q, all these problems for every Q in the class, is there some kind of complexity dichotomy, right? Now, first of all, just to notice, this is a problem that has been studied before. There's a varied complexity landscape, so it's clear that for every first order query, this problem is in coend P, because if the answer is no, then a repair is a succinct certificate for no. For some queries, and that will be the focus of the paper, the complexity is in FO. So FO is here the complexity class of problems that take a database as input and that can be solved by a single first order query. So for example, if I take this query, is Mons in Belgium, then actually this can be solved in first order, because this is like the first order query that solves the problem. You just have to ask whether Mons is in FO, and there's no tuple in the database stating that Mons is in another country, right? It's also noted that there are queries for which the complexity is in P minus FO, and for some other queries it's coend P complete. So we have all possible complexities depending on the query. So it's more than 15 years of research, starting with the famous ABC paper by Marcelo Arenas and others. And here we focus only on primary keys. There has been a lot of work on conjunctive queries, self-joint free conjunctive queries, which finally we got a P coend P complete dichotomy for this class. There has been work by Kolaitis and Inalea Pema, by Kutris and Sushu, by myself. And a lot of work on conjunctive queries, and maybe one of the reasons why this is the case, that Gaël Fontaine showed that if you find a P coend P complete dichotomy for union of conjunctive queries, then this implies Bulatov's complexity dichotomy for conservative speed. So that's probably one of the reasons why most of the work has focused on conjunctive queries. So what is the focus of this paper and the main result? So in this paper, we are looking at conjunctive queries with negated atoms, right? So these are queries of this form where you can possibly have a negated atom. And here's an example. Suppose you have two relations R and S. Here you have girls and boys. And the primary key is always underlined as X is Y. And you can look at this as Alice can choose between Bob and Ed can choose between Alice and Maria, and so on. And then you can look at this as a matching problem. So you have an arrow from Alice to Bob because Alice can choose Bob and vice versa. And then actually the query asks whether there are R tuples that without matching S facts, so whether there are unmatched R facts. So if you look at this as a matching problem, then if you look at the repair, in this case you have a repair falsifying the query, because here for every R fact there is the corresponding inverse S fact, and this actually corresponds to having a matching for this two-dimensional matching problem. So this already shows that the two-dimensional matching can be reduced to the complement for certainty Q. Okay, so what are Boolean queries with negated atoms? These are expressions of this form where you have positive atoms, negated atoms, and always you have this safe negation, meaning that every variable that occurs in a negative atom should also occur in a positive atom. Often we just represent it as the Q plus is a set of positive facts and Q minus is a set of negative facts. Such a query is self-joint free if no relation name occurs more than once, and so in this paper we only focus on self-joint free queries. And importantly, negation is guarded if for every negative atom there exists a positive atom, a guard that contains all the variables of the negative atom. And in this paper we introduce another notion of guardedness, which we call weakly guarded. We call a query weakly guarded if whenever two variables occur together in a negative atom, they should also occur together in a positive atom. So you can see that weakly guarded is somewhere between safe and guarded. So this is just so this is the class of queries. We are looking at self-joint free Boolean conjunctive queries with 0, 1 or more negated atoms. And then the main result of this paper is the following, that this problem is decidable. So the input is query Q in this class with weakly guarded negation, and the question is whether certainty Q can be solved in FO, right? And also, if the problem is in FO, then the first order expression for solving certainty Q, what it's commonly called a consistent first order rewriting for the query, can be effectively constructed, right? So now I will go more into some technical details. So how did we prove this theorem? The outline is as follows. To each Boolean query in the class, always with weakly guarded negation, we associate a directed graph, which we call the attack graph, whose vertex set is the set of atoms in the query. And then we showed two things, that if the attack graph of the query is cyclic, then the problem is Lockspace hard, and otherwise we can solve it in FO. Now I won't go into details about the attack graph. Some of you might know this from previous paper. Actually what we did here is like an extension of the attack graph to take into account negated atoms. If you want the technical details, they are in the paper and also on the poster. So how do we show Lockspace hardness computations? Well, we just have three basic queries, like Q0 without negated atoms, Q1 with one negated atom, and Q2 with two negated atoms. And we showed that for each of these three queries, it's the problem certainty Qi is Lockspace hard. And then we generalize this result. So whenever we have a attack graph with a cycle, then we have a first order reduction from one of these three problems to the query that has a cyclic attack graph, showing so that cyclic attack graph means that the problem is Lockspace hard and so not in FO. So in the remaining of the talk, I will focus more on the FO part. So how do we get first order rewritability? So I go here in a number of steps. So first, take the most easiest case where all the relations are all key. All key, we mean that the primary key contains all the attributes of the relation. Then it's clear that, so all atoms of this form, and then it's clear that the database is its own unique repair. There's only one repair. And then it's obvious that testing whether the query Q is true in every repair is just testing whether the query Q is true on the original database. So that's really the trivial case, right? And then the next case, it's a little bit more complicated, is suppose we have a primary key that contains no variables. So it's of the form RC or the negation of it. But C contains no variables. So I will note Q prime is Q minus this atom with a variable free primary key. And then you can easily see that suppose first that it's a positive atom, then if Q is true in every repair of the database, then the following should hold. That there should be a fact of this form, a block whose primary key is C, and then for every fact in this block, it should be true that Q prime n y equal to b is true in every repair of the database. So somehow you test for a block, and then you have a universal quantifier running over all the facts of that block, right? And this you can express in first order logic, right? And if you have the negation of an atom, then it's almost the same, except that in this case, you should check whether Q prime is true in every repair, and then whenever you have a fact of this form, you should check that Q prime n, in this case y, should not be equal to b, should be true in every repair, right? So, and these are conditions that you can test in first order. Yeah, there's one minor issue here. Here we are testing a negation of an equality. You can simulate this also in the framework again by adding a new predicate to your query, which is a negated one, and to the database you add the fact that contains the constant. So in this way you can add this equality into the query to remain within the framework. Now the most interesting case is, of course, when every primary key contains at least one variable. Yeah? So assume you have an atom like this, where S contains at least one variable, and assume that X is the sequence of the variables that are in the primary key. Then we have a notion of what we call reifiability. So we say that X is reifiable in the query if the following are equivalent. If Q is true in every repair of the database, then there exists constant C such that Q n X equals C is true in every repair of the database. So this means that if the query is true in every repair, then it's true for a fixed value of X, right? And then, of course, if you have such a reifiable primary key, then you are back in the previous case, right? Because with the first order rewriting, you can reify the primary key, and then you have a primary key without variables, right? So what we actually showed is that this notion of reifiability, it's a decidable notion. So if you are giving a query Q in our class with weakly guarded negation and a sequence of variables, then we can decide whether X is reifiable. And this finally leads us to the first order algorithm, which is sketched as follows. So it requires that Q is a self-joint free Boolean conjunctive query with negated atoms and weakly guarded negation. And then we simply test if all the atoms of key of Q are all key, then of course we can just execute a query on the database. Otherwise, we pick an atom such that all variables in the primary key are reifiable. This means it can be reified or the primary key contains no variables, and then we apply recursively the computation that I showed on the previous slides. And this actually solves the problem in first-order logic, right? Now, of course, at some point, you may say, what happens if no such atom exists? So if there's no such atom whose primary key is reifiable, well, in that case, we can show that the attack graph will contain a cycle, and so the problem is Lockspace hard, and we are done also, right? So what is actually, to summarize this, it means that if you have queries with weakly guarded negation, then whenever certainty Q is in FO, you have a very nice rewriting style where you pick repeatedly an atom or a negated atom whose primary key can be reified. You have an existential quantification, and then you have a universal quantification that runs over all the tuples of the block, right? And then interestingly, and now I come to the point, why do we need weakly guarded negation? It turns out that this style of rewriting is no longer sufficient if the negation is not weakly guarded, right? So because if negation is not weakly guarded, then there exists a query, and I will show such a query on the next slide, so that certainty Q is in FO, but there's no atom whose primary key can be reified. So it means that the rewriting style we developed is no longer valid here. And such query, any such query, must have negation that is not weakly guarded. Right? I show you an example here. So assume this is the query x, y, y, and then we have two negation, not x, r, x, y, s, y, x. Right? Here you see that the negation is not weakly guarded because x and y occur together in a negated atom, but they do not occur or get together in a positive atom. Right? It may be useful to think also about this query. The negation of this query can be expressed like this for all x, for all y. If x is x, y and y, then one of these two should be true. That's just the negation. Now, if you look at this database, then it can easily be seen that every repair satisfies the query, right? And why is this? Because you have here, of course, these relations are consistent, and you have 6 possible combinations for x and y to make the query true, whereas there are only 5 blocks. So you will always, whenever you make a choice for x and y, you will always find that not q will be false and q will be true, right? Now, in this query, you can also see that neither x nor y is reifiable. For example, if I try to, in this case, I fix the value of x, that's the idea of reification, then there is a repair that falsifies the query. In this repair, it's just sufficient to pick the tuples that are indicated by the block, so A1, B1, because then for every possible value for y, I have the two values. I have A1 and B1 in the repair, so the query will be false in that repair. And this holds also for any value you try to fix, right? So this means that this query is true in every repair, but you cannot fix x or y, right? So this means that our rewriting style does not work on this query, and yet it can be seen that this query must be in FO, is in FO, but it uses a kind of counting. It's easy to rewrite it in FO, but it's another rewriting style. So to conclude this paper, so we showed that for every query queue in this class with weakly guarded negation, it's decidable whether the problem is in FO, and if it's in FO, then we can construct the FO rewriting, and if not in FO, then it's L hard. And actually, this rewriting has a very nice rewriting style, which does no longer hold true if the query is not weakly guarded. So open problems is, of course, how do we deal with negation that is not weakly guarded? And maybe even more ambitious is like show that for this set, you also have a P-QMP dichotomy, no matter whether it's weakly guarded or not weakly guarded. Okay, this concludes my paper, my presentation. This is just a lower bound because we have queries for which this problem is QMP complete. Yeah, because if you have no negated atom, you are just in the conjunctive queries, self-doing conjunctive queries for which you have a PQMP complete dichotomy. So. I don't think it's exactly the same. Oops. Sorry. There are different notions of guardedness in logics, right? And I think in the related work section we made some comparisons with existing notions of guardedness. But I think it's not exactly something that is already known or present in the literature. Hmm? I think most common notions are just the guarded notions, completely guarded. But we don't need it. We only need that somehow that the variables are pairwise guarded. Yeah.
I think you showed somewhere that if you have inequalities, you can simulate.
Yeah.
Suppose now that we have only inequalities. You know something more about this class? Just conductive queries with inequalities.
Ah. I'm looking at Paris. No, you don't. I don't see immediately. It's a nice question, but we actually do not deal with this equality. It just shows up, and we need to handle it. But yeah, I don't know what happens if you have.
Positive results, they apply.
Hmm? Yeah. Because you can just have no negated atom. Yeah.
No, but you don't have any more. The queries are meaningful even if you don't have the guarded or non-guarded. Just have inequality.
Yeah. I don't know. I don't know. Yeah. If you have. I'm not sure that I understood what kind of constraints you have in mind.
So actually is a relaxation. So it's different kind of data model. So within this data model you have a key that maps to a value and that's okay. Then I'm thinking of a data model where you have key, value and negation of the value. That could state, for example, I could have any possible value but not this.
Yeah, I understand. Here you are somehow saying that like these are the only possible values, and you want to now to. I cannot think like this of a common sense answer, so I'll think about it.
Okay, so plenty of interesting